All right, so welcome to another video. We are still in chapter 1. We're in section 7. And before we jump in, I want to kind of recall. Do you recall back in section 1.5, we were discussing the concept of homogeneous equations, right? So really quickly, we had discussed homogeneous equations looked something like this, right? Where we had some matrix A, some vector X, and we had discussed, which in which ways are solutions available. We had discussed things like, are there only trivial solutions, or are there more than just trivial solutions? And what I want to do now is I want to kind of study this idea from a different perspective. All right, so from the perspective of a vector equation. So let me introduce the vocabulary that I'm going to be using a lot this lesson. And what you really should do is you should write this down and have it readily available. So when I say linearly independent, linearly dependent, think, a few pages from now, if you start to mix them up or forget exactly what it is I'm saying, you can refer back to that little vocabulary sheet. But nevertheless, let me go ahead and jump in. So let's start with the idea of linear independence. Okay, so the way this begins is we start with some set of vectors, right? So imagine that we have a set of vectors and a set of scalars. So it's already written above, but just to rewrite it, so we could have, say, I'm going to, here what they're doing is they're using x sub 1 to represent the scalar portion and the v to represent the vector. Okay, so x sub 1, v sub 1, plus x sub 2, v sub 2. Now, I could keep going because this can be extended to more than just two vectors. But nevertheless, the idea is that it's equal to 0. Now, the other type of relation, dependence, linear dependence or linear relation, is that of linear dependence. And again, I'm going to write the same thing twice. So x sub 1, v sub 1, plus x sub 2, v sub 2 equals 0. Now, so what is it that makes the following equation linearly independent or linearly dependent? Well, let's think of it like this. So imagine that we have some defined vectors. Okay, I don't know what they are. Just we could be 1, 2. We could be in two dimensions. We could be in R3. Doesn't really matter. The question is, what are some ways, what are some possibilities? And we will assume that these are non-zero vectors for right now. Okay, what are the possibilities for making the following equation a true statement? How do I get to 0? So the only thing that you have at your disposal is you can choose different scalars, right? You can choose any scalars you want. You can even choose 0. Now, if the only way you can make this equation equal 0 is if you choose 0 for x sub 1 and x sub 2, right? Like, there's nothing else. 0 times v sub 1 plus 0 times v sub 2, of course that equals 0, right? 0 plus 0 is, of course, 0. That is our definition from the previous section, from 1.5. That is the definition of the trivial solution. Now, if all you can do is choose weights of 0, choose scalars of 0, in other words, all you have is the trivial solution. If that's it, then your relation is linearly independent. Only the trivial solutions. Only weights of 0. However, If there are other scalars other than 0, other than 0, 0 in this case, if there are other scalars that you could plug in to equal 0, then your relation is linearly dependent. So imagine for a second, imagine that you chose, my apologies, imagine you chose 1 for x sub 1 and you chose -2 for x sub 2. And somehow when you multiplied v sub 1 times 1 minus 2 times v sub 2, imagine that zeroed out. Well, in that case, you found weights, 1 and -2. You found scalars that would make your equation equal 0, aside from just choosing 0, 0. So, linearly dependent, more than just the trivial solution. Linearly independent, only the trivial solution. That's kind of the informal yet, index card approach to these definitions. So I think the best thing to do is to jump into the example, and let's practice the vocabulary. We'll stay here for a second because, again, it's hard to follow. If I keep using the word independent and I use the word dependent and you still don't know what I actually mean by that, then that's going to be a problem later. So the following example, we're given 3 vectors, right? V sub 1, V sub 2, V sub 3. And notice that each vector is in R3, right? So this is, you could, again, for my engineer science people, you can think of this as like I, J, K, right? We have 3 components here, and then we are in 3-dimensional space, and we also have 3 vectors. In other words, this is not an aside. I think this will come in handy in a little bit. Let's notice something. Let's notice that the number of vectors is equal to 3. And of course, you recall that this is an n by 1 matrix, right? So, in other words, this is a 3 by 1 matrix. This is a 3 by 1. This is a 3 by 1. So a vector can be thought of as a matrix of 1 column. So the number of entries here, right? The number of rows, in other words, n, is equal to 3. I promise you this is going to help in just a second. So let's just stay with me. 1, 2, 3 vectors. And the vectors are in 3-dimensional space, 1, 2, 3, so n is 3. Okay. Now, what do they actually want from us? Well, part A, it says determine if the set of these 3 vectors is linearly independent. In other words, determine if only the trivial solution works. So let's set up the vector equation here, right? So let's go ahead and use x sub 1, and for v sub 1 I'll have 1, 2, 3, and that would be plus x sub 2 times 4, 5, 6 plus x sub 3 multiplied by 2, 1, 0, and that is set equal to 0. Okay, so the question is asking, determine if this set is linearly independent, meaning the only way to make this equation equal 0, the way you can do it is if you choose scalars of 0. 0 plus 0 plus 0, right? If that's the case, then yes, it is linearly independent. If that's not the case, then we answer no to this question. Well, the most beautiful thing about linear algebra is this interconnectedness between vectors and systems and matrices, and how we can just seamlessly just go from one way of looking at a problem to another way. And what we're going to do is we are going to set up a matrix. And then we are gonna row reduce this matrix. So just so you know that the columns of the matrix are going to be formed from the vectors. I'll say that again. So our column 1 in this matrix is going to be formed from the first vector, 1, 2, 3. The second column of this matrix is formed from the next vector. And then the third vector forms the third column. Now, so far this is a coefficient matrix, right? It's not an augmented matrix. But we are going to make it an augmented matrix because this last column, this is formed from the 0 vector. Just again, you've probably heard me mention before, but the 0 vector, okay, is going to change depending on the context. So, in other words, this is 0, 0, 0. So what I'm going to do in a second is I'm going to erase the 0, because what they really mean is the 0 vector, which will be written as follows. So let me go ahead and write the 0 in the context of this problem. So if we were dealing with two-dimensional vectors, then obviously our 0 vector would be written like this. But we are in 3 dimensions, so our vectors are going to be written like as follows. So the very last column here is going to be formed from that 0 vector. Now at this point, you know, this problem never mentioned anything about matrices, right? I mean, this problem's talking about scalars and it's talking about vectors. But lo and behold, we can view vectors this way, and this allows us to use some technology, right? We can row reduce the following, and I'm gonna go ahead and do that right now. So what I would get is the following. Now, you could answer part A from where we are right now. However, until you get pretty good, like just imagine for a second, just imagine that this is what your calculator says, all right? This is your screen. Now, in a little bit, if not already, you will be able to answer questions like A just from this screen on your calculator. But until then, until you become proficient with this, what we're going to do is let's turn this matrix back into a system. Okay? So we're going to write the general form, which is okay because it's going to help us with part B anyway. We'll write the general form of the solution. So if we take a look at, in terms of pivots, we have a pivot position here. We have a pivot position here. So the first 2 columns are pivot columns. But notice there's no pivot position for the third column. Now that tells us that this is the free variable. So we got a basic variable, free variable. So we're going to solve for the basic variables. Right, so basic variables, that would be x sub 1, x sub 2. X sub 3 is going to be the free variable. So let's go ahead and do that. So x sub 1 is equal to, well, you got to imagine, again, until you've gotten good at this, so this is 1 x sub 1. If we solve this equation, think about this as this whole row, think of it like an equation. This is your equal symbol. So then we're going to take this negative 2x sub 3, and we're going to bring it over, okay? So in other words, we have x sub 1 is equal to positive 2 x sub 3. We're going to do the same thing here. So this is 1x sub 2 plus 1x sub 3 equals 0. And again, we're going to solve for that basic variable, so we're going to bring that over too. So in this case, x sub 2 is equal to negative x sub 3. And finally, the x sub 3 is the free variable, and we must state that it's the free variable. So if you recall, in section 1.5, when we were discussing homogeneous equations, we basically had come to the conclusion that, look, if you have free variables, then you have non-trivial solutions. If you have free variables, you have non-trivial solutions. In other words, just to make up something here, let's say that you chose, remember, because x sub 3 is free, so let's say you chose x sub 3 is, I don't know, 5. Well, then x sub 2 would be negative 5, and x sub 1 would be 2 times 5, which would be 10. Listen to me, if you haven't checked out yet. If you take 5 and place it here, you take negative 5, place it here, and you take 10 and place it here, when you do the math out, you will get 0. So there are other ways to get 0 than just choosing zeros as the scalars. We just found this is one of many. So determine if the set of these 3 vectors is linearly independent. Well, the answer is no. They are not linearly independent. If they were, then only 0, 0, 0 would have worked. So this is no. This is not linearly independent. Now, the good news is we've already kind of done most of the heavy lifting for part B. So part B says, look, if possible, meaning it's not linearly independent, so if possible, find a linear dependence relation among these 3 vectors. Now, can you imagine getting to a test and freezing up with this statement? If it's not linearly independent, find a linear dependence relation. What that means is find a solution to the equation other than just 0, 0, 0. And that's exactly what we did. 5, negative 5, 10. That works. So here's the way they would want that written. So all I have to do at this point is just write 10 v sub 1 minus 5 v sub 2 plus 5 v sub 3 equals 0. That's what we just said. If you plug in 5, negative 5, 10, this here is the relation among the linear dependent relation among these 3 vectors. This is the answer to part B. Okay, so my hope is that the vocabulary is not getting too dense yet, but what I want to do is I want to go over, because the idea is it's hard, if I don't have you in class and I don't have you to ask me questions or to repeat something, then I'd want to make sure you understand some statements. Let me tell you something. When I go through these, if you understand everything that I'm saying, or like even can anticipate what I'm about to say, then that is a beautiful sign. Okay, that means you really are starting to understand this. So let me start. So it says, so a set containing, well, we'll start with one vector. So a set containing one vector is linearly what? Well, again, I could just give you answers, but that doesn't quite help you. Let me write some set containing one vectors. Ready? So that would be something like x sub 1 times v sub 1 equals 0. And I'll tell you what, I'll make up a vector. Let's say x sub 1 multiplied by vector 1, 2 equals 0. Okay. Now, if you were to plot, if you think about plotting that out, and the geometry is important to me. If you think about this as a point over 1 up to and of course this is the vector, right? Now you can scale this vector. Now scaling it, does it make sense to you? Because I'm trying my best. This is the best that I can do to try to help you understand what is quite which can be quite a formidable subject. I just want you to understand that here's the vector 1, 2. Now you agree that I can choose a scalar. Like I could double that, right? I could choose 2, and now it would look something like this. Or I could choose -2, right? It might be down here. In other words, since I can choose any scalar, don't you agree with me that that's some some line running through the origin? Agreed? Now, of all of those, remember, every point on this line is just you choosing a different scalar. Of all of those points, do you agree with me that there is only one way? There's only one way to get it to equal 0. And that's if you choose 0 for your scalar. Right? Don't you agree with me? The only time this line crosses 0 is when you choose a scalar of 0. In other words, it's the trivial solution. So a set containing one vector is automatically linearly independent. You can only make this vector equal 0 if you choose 0 as a scalar. Now, again, we are assuming that the vector itself is not the 0 vector. Right? So that's the next question. So a set containing the 0 vector. Now let's go ahead and write that. So remember, you could choose any scalar you want to, but this time your vector itself is the 0 vector. Now, do you agree with me that no matter what you choose for your scalar, anything times vector 0 is always going to equal 0? So you could choose 0 for your scalar. That would be the trivial. That would be true. You could choose 1. 1 times 0 is 0. That would be true. You could choose 2. You could choose 3. You understand that you have more options. In other words, a set containing the 0 vector is always linearly what? Dependent. There's a whole bunch of, there's an infinite amount of scalars. Choose any scalar you want to. It'll always equal 0. Okay. Now, unit vectors are always linearly, well, let's make sure we understand a unit vector. So a unit vector would be, it would mean that its magnitude is 1, right? The unit, just like the unit circle has a radius of 1. So this is a unit vector. Now, unit vectors are always linearly independent. It doesn't matter. It doesn't matter what space that you are in. Okay, it doesn't matter if you're in 2-dimensional, 3-dimensional, etc. Unit vectors, the only way to make this equal 0 is if you chose 0. So unit vectors are always linearly independent. Okay, so